Hi, everyone. My name is Anthony Molinaro. I'm the co-author of the paper you see on your screen with Frank DeFalco. I work with Frank and Claire Blackadder and Dimitri Dimshitz at Janssen. We form a team called DISCO. That stands for Data Integration, Standardization, Characterization, and Operations. We work in Patrick's department in ODA. OHDA stands for Observational Health Data Analytics. And before diving into the paper, I'd like to give you a little bit of a background as to why we publish this paper, why it's important, what it has to do with a lot of the themes you may have heard about on various calls, why certain packages exist in the Odyssey repo. So if you're new to Odyssey, or if you've been here for a while, you know that the Odyssey community is really at the forefront of methods development and methods research. And if you don't mind the silly analogy, an expert in methods development is sort of like a master chef. And but even a master chef, if you have rotten eggs and spoiled milk, would have a hard time making a nice meal. So the meal depends not only on their ability, but on the quality of the ingredients. Likewise, if we want to generate reliable evidence, we have to have reliable phenotypes, which in turn depend on reliable cohorts, which depend on reliable concept sets, which depend on reliable concepts. So have this in the back of your mind as I explain what we're doing and why we do it. Frank and I were investigating concept IDs, concept time sets, and concept time series, and we observed that the prevalence would bottom out. It would go to zero. There seemed to be normal fluctuation and then just disappear. And we found out that in some cases if it was a drug, there might be an FDA warning on the ingredient, or if it was a concept, maybe there was a code switch from ICD-9 to ICD-10. But sometimes that prevalence would go to zero and then come back up again, and then back down to zero and up again. And we observed that there was cyclical behavior in these time series. So in an effort to characterize these changes and provide the information to the group that's developing the phenotypes and cohorts, we thought the low-hanging fruit would be to identify what was seasonal in the time series, which time series was seasonal, and from there back into something that would detect some sort of anomaly or change point. What we found out immediately was that there are many methods that were developed to classify a time series as seasonal. These methods were developed almost over 100 years, and they didn't agree with each other. And so when we observed that, we decided to do a more systematic study to increase the number of databases, increase the number of methods we were looking at, and also we wanted to look at different levels of significance and determine whether or not if the disagreement between the methods was localized. Okay, so with that said, I'll jump right into the paper and get this. So the databases we used are listed in table 1. I won't walk through them one by one, but you can investigate this. We had a number of databases. We tried to have a nice mix between claims and EHR, US and non-US databases. The particular methods we compared are listed in table 2 of the paper. And this table 3 here is a great example of what we initially saw. So this is on the top row is abbreviations for the different methods. And each row of data represents the results for one database. So PHD is a premier healthcare database. And you could see the QS method identified 30.5% of the time series as seasonal, but the AA, or the auto-ARIMA method, identified 79% as seasonal. Because of this large discrepancy, we wanted to give the methods the benefit of the doubt. So we defined agreement or concordance as a situation where two different methods would classify a time series as either seasonal or non-seasonal. So as long as they agreed, we didn't really care if the method determined the time series was seasonal or not. The issue is whether or not they agree. And this was important not only because of what you see on your screen with this large variation within databases, but also the proportion can hide the truth about the classification. For instance, if you and I have 10 time series and I classify half of them seasonal and so do you, we can't assume we classified the same half, right? I may have done the even ones, you may have done the odd ones, for example. So it was very important to not only look at the proportion of time series classified seasonal or not, but which time series were classified seasonal. So across all databases, I'll expand this a bit. This figure shows across all databases, all levels of significance, the amount of concordance that we found. So this is a stacked bar chart. The green bars represent the proportion of time series considered seasonal, and the red bar represents the proportion of time series considered non-seasonal. If you combine the red and the green, that gives you concordance, how often they agreed. And unfortunately, the orange is the discord, how often they disagreed. And what we find is the concordance, or the universal agreement across all methods, databases, and levels of significance is ranged from 20 to 40%. This means that roughly 60 to 80% of the time, the methods disagree. And the implications of this are the following. In this figure here, we have a 3x3 plot of some time series. From left to right, we have on the top of each plot is each method, and we use a color coding scheme, green to indicate that the method determined the time series is seasonal, red to indicate that the particular method said this time series was not seasonal. And if you look at this top row, the time series look very similar. I don't think you could visualize them and you could tell in advance which time series we're going to say which methods we're going to determine seasonal and non-seasonal. Likewise for the bottom row. In particular, if you look at the y-axis, I know you could. This is a close-up, and so it looks like there's a linear trend. The trends were removed, by the way. But if you look at the y-axis, these time series are essentially constant. But why would there be a disagreement at all? What's seasonal about these to this method or this method? And so this is the implication of this work. And so the consequence of this is two researchers using two different methods are very likely to get different conclusions. And this affects the generalizability of the work. So moving forward with this knowledge, the researchers should list their choice of method as a limitation of their study. And that's it. If you have questions or comments, I should have added that we developed this entire study using Achilles and a package called Castor. This is all in the Odyssey GitHub repo. Okay, thanks.